So hi and welcome everybody to session number 3 on error control coding. So we will continue from where we left off from the previous session. We talked about linear block codes and how they work at the transmitter and the generation process and how they are how you can relate the code word to the message sequence and the generator matrix, how to build it. Now we need to exactly learn in details how we can build the circuit responsible for generating the code words for different types of messages. So let's give an example, and let's say we have the message sequence given to us is shown as follows, and the sequence can be u0 is equal to 1, let's say, and u1 is equal to 0, u2 is equal to 1, and u3 is equal to 1. Yes, and now we need to encode this. To encode this, and of course we are using 7374 block code. 7 means N and 4 means K, and for this example the code rate R is equal to 4/7. This is the R value we have. Now we need to encode it so you can call this U vector, the message sequence, and you need to get V vector. V is equal to V here, you can define it also as a vector, which is equal to V0, V0, V1, V2, V3, V4, V5, and V6. Do you have V7? No, because you have only 7 elements. N is equal to 7, and since it starts from 0, then from 0 to 6 you have 7 elements. Okay, now if I tell you this is this code, the block code we are using for error control correction, it's basically systematic. If I say systematic, then you immediately take these 4 bits from the message, the 4 bits from the message, and you put them here at the output. You take them from the message 1 0 1 1, and you put them here for these 4 values. So now you can tell me, since I said that systematic, this means that V3 is equal to U0, V3 is equal to U0 and it's equal to 1, and V4 is equal to U1 and it's equal to 0, and V5 is equal to U2 and it's equal to 1, and V6 is equal to U3 and which is equal to 1 2. So then you put in the sequence V. You tell me now the sequence V is given as follows. V, the new V I have V0, V1, V3, I don't know their values, but I know the values of the remaining ones. V3 is 1, here I have 1, V4 is 0, V5 is 1, V6 is 1. So this is the code word at the output. Up until now I have this. But what about V0? What about V3? What about V1 and V2? V0, V1 and V2. I need to determine their values. Should I put them 0 or 1? I need to know that. How do you know that? How do you do that? You just go to you go to the circuit that we built to generate the codes. The circuit for V0 you need to look here. For V1 you need to look here. For V2 you need to look here. What's V0? V0 is the XOR operation coming from these three lines. 1, 2, 3. Could you please tell me this line from where is coming? This line is U0. And this line is coming from U3. And this line is coming from U2. So V0 is equal to, you tell me it's equal to U0 XOR U3 XOR U2. Okay. What's U0? U0, I define it to be 1. I give it to you. What's U3? U3 is also 1. What's U2? U2 is also 1. 1 XOR 1, 0. Yes? XOR 1, 1. Then V0 here, the result is 1. Okay? Now let's go to V1. What's V1? V1, let's delete these. V1 is coming from we have these three lines for V1. Let's focus together what V1 is. We have this line. This line is coming from where? From U. From U1, U0. So here we have U0. And this line is coming from U1. You have U1. And this line is coming from where? From U2. So U0, U1, U2, XOR them with each other. So you tell me V1, which is this is equal to U0 XOR U1 XOR U2. And what's the value of U0? U0 is 1. U1 is 0. And U2 is 1. You XOR them with each other. And 1 XOR 0, 1. XOR 1 equal 0. So V1 is equal to 0. Here you put 0. We finished V1. We move to V2. Let's delete these. And move to V2. V2 has also three lines coming in, and these three lines we need to determine what they are exactly. So let's go to V2 here, different color, use red. So here the first one, this one, let me delete this because it's not showing. We don't need those now. This line, the first line, is coming from U2. U2. Here I have U2. And this line is coming from U3. This line is coming from U3. So here you have U3. And this line is coming from U0. So U0, this line this line U1. So you have V2 here. V2 is equal to U1 XOR U3 XOR U2. So U1 is 0, U3 is 1, U2 is also 1. XOR them 0 XOR 1 1, 1 XOR 1 is 0. This is 0. So V2 is equal to 0. Here I have 0. So what's now you were able to find V0, V1, V2, V3, V4, V5, V6. And if I ask you what's the code word that you need to transmit over the channel, you tell me V, which is given as shown below. 1 V is 1 0 0 1 0 1 1. This is the code word representing the message sequence 1 0 1 1. To check this, whether it's right or correct, and be able, this circuit is built using the generator matrix G. Yes, not H, G. So when you go back, let's go back to the slides. When you go back, you don't look at this. You don't look at this slide. You look at this slide. This slide. This slide shows you G. And from this matrix, you can find V0, V1, V3, V0, V1, V2. And this G is basically implemented with the circuit that you see here, and from which you can be able to find V for any information sequence bit. Okay? This is very critical and very important, and we need to be very careful about it. So now you know how to encode your sequence. If I give you another different sequence, not 1 0 1 1, if I give you 0 0 1 0, the answer will be completely different, and you need to recalculate this again. Of course, if I say systematic code and you don't make use of this fact, you will not be able to finish on time. So it might take longer period of time, and you might not be able to even find the answer. So to simplify this for you, I usually tell you that this is systematic encoder, so that you don't spend too much time finding all the values using equations. You just need to find the first 3 values, and then the remaining you put the information exactly as they are in the code word. Okay, can we move on? We can move on. Let's see. The information symbols are pushed to the channel. In the meantime, they fill in the delay elements. Delay elements here, which are the squares here in the circuit. Now consider for the block code we have NK with generator matrix G and parity check matrix H, and we know the relationship between H and G. Yes, you know the relationship that you basically flip the matrix. You transpose it. Assume that V is equal to V0, from V0 to Vn minus 1 is transmitted over a noisy channel, and R from R0 to Rn minus 1 is received at the decoder. This is now what we have. Let's summarize what we have done so far. You have U as the transmitter. Then using the generator matrix and the encoder circuit, you got V, and then V you transmitted through the channel here through G, the generator matrix, you got V, and through the channel, the noisy channel, you get what? You get R. Now R is equal here at this stage, R is equal to V plus noise, and those both are vectors. And you need at the receiver side, we are at the receiver, we receive this, and we want to determine from R. We don't know V, we don't know noise. You don't know V, nor you know N, but you only know R. From R, you need to guess what was V. Let us define E, which is the error vector, and E is defined as follows. E is equal to R plus V. R plus V is equal to the error caused by the channel. The noise produced by the channel can flip the bit from 0 to 1 or from 1 to 0, where EI is equal to 0 for RI equal VI and EI equal 1 for RI not equal to VI. For all I values, the vector E is called the error vectors. Now, why did I define E in this manner? E is equal to R plus V. Simply because V is the original code word, and you transmit it, and you receive it at the receiver as R. R is basically summed to the noise. The noise summed to the code word. For example, the noise can change some bits from 0 to 1 or from 1 to 0. Any change in R, it's supposed to be V. If it changes to some other values, then you will have ones in the vector E. Ones means there is an error. Let's say V was something like this, 1, 1, 0. And due to noise, you didn't receive it like this, you receive it like this, 1, 1, 1. Where is the error? The error in the third bit, 1. Now, when you XOR them with each other, yes, this is V, this is R. 1 XOR 1, 0. 1 XOR 1, 0. 0 XOR 1, 1. Here you know that here there is an error caused by the channel. If you know that this is an error, yes, this is an error caused by the channel, and you only have 0 or 1 values, then you just flip this back to 0, you get the correct code. If you are using only 0 or 1. This is how you detect and correct. This is just one simple approach, but you have many different approaches. Some of them, they are extremely very complex, that we will explain them in the coming lectures one by one. But for now, you understand how to relate the code word to the received vector and define error vector that can tell you whether there is any error or not, and how to detect it and how to correct it. You can correct it using this simple method only if you are using what? If you are using binary digits, 0 or 1. But if you are not using binary digits, you cannot correct it using this simple method. So we can also write R, the received vector R is equal to V, which is the code word, plus the error E. Now, the decoder at the receiver side must first determine whether any error has occurred during a transmission. This process is known as error detection. Please remember this. Error detection process is done at the receiver side during the decoding process to determine whether there are any errors or not. It first to do so this is the other approach, the systematic approach that utilizes the generator matrix and H matrix at the receiver. What do? It first computes S. S is equal to R multiplied by H transpose. How do you obtain H? H you obtain it from G. And R, you received it at the receiver. From this, you can calculate a vector called S. This vector, it has a special name. We name it syndrome. Syndrome is the vector resulting from the multiplication of the received vector with the matrix H transpose. If S is equal to 0, if and only if R is a code word. If R is a code word, it belongs to one of the code words, then S is 0. You always have S is 0. If if the syndrome is not equal to 0, an error is detected. Okay? So this we call it absolute error because you are detecting a code outside of the range of codes you used at the transmitter, and this you detect a code among all the used code at the transmitter, but you don't know which one is really the correct one. That's why we move on to the other steps that can help us determine this. First steps towards error correction. So first, initially you detected that there is an error or not. If the syndrome is equal to 0, R is a code word. If the syndrome is not equal to 0, an error is detected. First steps towards error correction. This is where you start correcting after you detect that there is an error. This is the first connection between the transmitted code word and the received vector. The syndrome is the connection between them. Now, keep in mind that neither V nor E, which means the code word and the error sequence, are not they are not known at the decoder. Only R, which is the summation of both V and E. And this is why we need encoding, and it's a little bit difficult than modulation and the other processes. Because you have the summation of two vectors, and from this summation you need to determine what was the vector, V, the code word. Does this mean we can detect all errors? If E is a non-zero code word, R is a code word, and S is equal 0. What does this mean? If E is a non-zero code word, if it is non-zero, this means that it has one element in it, 1, which means that there is an error in one of the bits. But R is a code word, and S is equal 0, which means that the code word belongs to the list of code words that we have used at the transmitter. And this means that there are 2 to power k minus 1 non-zero code words. There are 2 to power k minus 1 undetectable error vectors. Okay? From where is that coming? Because we said we have 2 to power k messages, but the number of different error codes is like 2 to power n, and you are not using all of them. You are using only subset of them, which is the number corresponding to the number of different messages you have. So among all these, you have 2 to power k minus 1 non-zero code words, and therefore 2 to power k minus 1 undetectable error vectors. Let's give an example, practical, realistic example. For the linear block code 7.4, you have the received code, the received message or the received signal R0, R1 till R6, and you have H which you obtained it from G. Then by multiplying R, the received vector, with H, you get S. S is the syndrome, and the vector length is equal to, the syndrome length is equal to n minus k. If n is 7 and k is 4, we have syndrome, length of the syndrome will be 3, as you can see here. So the syndrome S0, S1, S2 is equal to the multiplication of this vector with this column, and this vector with this column, this vector with this column. The first vector, the received vector with the first column gives you S0, which is equal to R0, R3, R5, R6. And S1, which is the multiplication of R vector with the second column is equal to R1 plus R3 plus R4 plus R5. This is R5. And S2, which is this element, S2 is this, is coming from the multiplication of this vector with the third column, which is equal to R. You don't have R0, you don't have R1, you have R2. R2 is here plus R4 because R3 is 0 plus R5 plus R6. So you have the syndrome here. You were able to obtain the syndrome. You can draw the correcting shift register based syndrome circuit similar to this circuit now from the three equations. See here we have V0, V1, V3. You can also draw a circuit for the syndrome similar to this, but instead of V's you put S. So here are the equation S, S0, S1, S2. You obtain them from the received vector R0, R3, You receive the bits in the vector, you put them in the circuit inputs, and from there you calculate S0, S1, S2. And this is the answer for this question. Draw the corresponding shift register based syndrome circuit. Now mathematically, how do you do that mathematically? Let's try to understand the significance of the syndrome S by math. S is equal to R multiplied by H transpose, as I showed you here. And the length of S is N minus K. Now, what's R? R, everybody knows that R is coming from the summation of V with E. V is the code word and E is the error caused by the channel on V. And you multiply it by H transpose, which is coming from G. But you just put the diagonal matrix element, unity matrix at the beginning and parity at the end, and you change the dimension. Then now you can distribute this. V. You can multiply V with H transpose and then E with H transpose. You get VH transpose, EH transpose. And since V with H transpose is always 0 because it's a code word, what will you get at the end? You will get E multiplied by H transpose. So the syndrome, when you multiply the received signal with H, as if you are getting this, E multiplied by H. These are equal. So S is equal to this, E multiplied by H transpose, and rewriting the syndrome equations for our example according to the new representation gives the following. For the 7-4 linear block code, S is equal to R multiplied by H transpose, which is equal to E multiplied by H transpose. This gives you these values that we already obtained previously here. So here S0 is equal to E0 instead of R. These equations are exactly the same as the previous equations I showed you here, but instead of R you put E. And this is coming from H. You put S0 equal E0 plus E3 plus E5, E6 and so on, and you continue in this pattern. You find S1 and S2. And then, even though the decoder does not have access to E directly, because it doesn't know E. It doesn't know E nor does know V. Both of them are unknown to the receiver. However, it can operate on it indirectly through the syndrome. From the syndrome, it can operate on it. So the syndrome S is available at the decoder. Yes, we can obtain it by multiplying the received vector with H transpose, which becomes equal to R multiplied by H transpose. Can we solve this equation set that we found here? Equation set, this one. We have n unknowns, n minus k equations. N minus k, which means for the case of 7-4, we have three equations. But we have 7 unknowns. And the solution for this problem, this we call it, we have infinity number of solutions. So we can reduce them to 2 to the power k solutions, because this is underdetermined problem. The number of equations are less than the unknown, and you don't have one. So how can you solve these? You have 2 to the power k different number of solutions. Now, depending on the channel, not all we can exclude some of the error vectors. Not all error vectors in this set are equally likely. The error correction step therefore must choose the most likely one. The most likely one, you choose them and include them in your solution. For a binary symmetric channel, for example, what do I mean by binary symmetric channel? Let me explain the binary symmetric channel this for you. In binary symmetric channel, you have, change the color, you can transmit 0 or 1. Now, if you transmit 1 and receive it wrongly 0, there is a probability for receiving it 0. We call it probability 0, 1. And there is a probability of receiving it 1 correctly. And the 0, if you receive it 0, we call that the reception is correct with a probability, with certain probability that we will write its value later on. And if you receive the 0 as 1, we call that you have made an error. And this error, we call it B10. So now, what's the probability of receiving your bit successfully? It's 1 minus B01. And the probability of receiving the 0 successfully is 1 minus B10, this one. So this channel, this type of channel, we call it binary symmetric channel. Binary symmetric because for 0 and 1 you have 2 different bits, and you have equal probability of receiving it correctly or wrongly. And if the probability of receiving it wrongly decreases, the probability of receiving it correctly increases automatically. So the maximum likely detection, let's explain the maximum likely detection. The maximum likely is a detection process that finds the closest code that reduces the error. Let me explain it to you. You have R, yes, you received R. R is equal to V plus E, yes? V plus error. So the detection, the maximum likelihood, it's something like this. You start guessing, you don't know V, you want to detect V, and you don't know E. So what do? You start guessing what would be the value of V that makes it very close to R. So you kind of define a new problem, R minus V plus E. This is the equation you have, and you try to minimize this value for all values of V. For all V, you try to search the value of V. You already have the possible code words that you think that the transmitter might have transmit. You have all the values of V's that the transmitter can choose and transmit to represent the message. So what you do is you search for the value of V that can minimize this result. You have R, you have V, E. So you don't know E, you know R, you received it, and V, you can obtain it from a mapping table or a lookup table, because you already know all the values that can be used, but you don't know which one of these values. So you define a for loop and you go over all of them one by one. and the one that gives you minimum result here, that reduces this value to minimum value, you detect it as this is the code word that the transmitter used to represent the message. And from here you detect that this was the code word. This is the simple this process of detection, we call it maximum likelihood. As you can see, it's complex process a little bit. Why? Because you need to search for all the codes one by one, one by one, one by one. Suppose you have 100 codes, you need to use all of them in these equations, calculate the results, and store the data in one element. And again, the second, the third, the fourth, until you finish all of them. And then you compare these all values and find the lowest value. And the code corresponding to the index of this lowest value is basically the code that the transmitter used. So it's very heavy and extremely expensive process in terms of complexity, and it can cause delay and consume lots of power. So it means that chooses V hat is the estimate after the ML detector. Chooses V hat as the code word V as the actual code that the transmitter used. That minimizes the distance D RV. Minimizing the distance RV is this equation. This word means this equation. This is equivalent to detecting an error vector E with minimum Hamming weight. Yes? Hamming weight is like the distance. Here it finds the distance, and because when you find out that the values of R and V, they are ones and zeros, so this becomes like distance. For example, if I tell you, you have this vector. What's the distance between them? Here you have 0, 0, 0. You have one square. Yes? How do you find the distance? Distance between these two vectors. It's the square root. It's the square root of the first element minus the second element, first element from the first code word minus the second element in the second code word. So 1 minus 1 square, 0, plus 0 minus 0 square, 0, plus 1 minus 1 square, 0, plus 1 minus 0 square, 1. Square root of 1 is equal 1. So the distance between them is 1. Now, if there is another error, let's say there is another error, instead of 0 here you have 1, you will get square root of 1 plus 1, which is square root of 2. The distance now is larger. So which code is closer? The one that has value 1 or square root of 2? 1, of course. That's why you select 1 to be the code representing the closest value. So let V equal 1001011 be the transmitted code word, and R is the received code word is 1. See, I transmitted V 1001011, but R, the received R, if I tell you where is the error, obviously you can detect clearly where is the error. Here is the error in this bit. Here there is an error in the channel. I need to correct that. The R is the received vector, but the receiver, since the receiver, the practical receiver, your smartphone, your smart computer, your whatever device you are using for reception, it doesn't know V. I know V because this is a question, because I designed the questions and I sent V. The receiver doesn't know V, so you cannot easily say that the error is here. The receiver only knows R, but he doesn't know V. That's why you cannot say simply the error is here. And therefore, we need to go through this complex process at the receiver to determine where is the error and how to correct it. Because I don't know V, I only have R. Now, at the receiver just right away tries to find the syndrome S, which is a vector of length k minus n, which is a vector of length n minus k, and it's equal to r multiplied by h transpose, and you already have r from the questions. You multiply it by h transpose. H, you know it. H, you get it from the generator, and you get that the syndrome is S111. Now, this syndrome, you can write these equations. S1 is equal to these values. S1 is coming from, S1 is equal 1, and it's equal to this. E0, E3, E5, E6. And S1 is equal to 1, and this is 1, and equal to E1, E3, E4, E5. And you do the same for S2. We can immediately see that the error vector is 0, 0, 0. After you do the calculation and calculate the values, you find that E is this. How is that? How did you find it? How do you make sure that this is correct? You come and add R to V to E. If it gives you the code, one of the codes, then this is correct. Once you add this together, you will get this V, and this means that this is the error. Now let's see what the decoder knows here. The following 2 to the power k equal 2 to the power 4 equal 16 error vectors satisfy this equation set. These are the equation sets that you obtained them from the previous values here. See how complex the process is, and it finds that E is equal to this value is the one with the smallest number of ones, and therefore the most likely one over a binary symmetric channel. Taking E as the estimated error vector, the decoder decides on V equal R plus E, and this is to find V. After you find the error E, you just add E to R and you find V, and you found out that V is this, which is this value that you transmitted here, V. But see how difficult and complex and time-consuming the process of detecting the bits at the receiver side. It's not as straightforward as you might think. Like for a human being, when you give him this, you transmitted V and you received R, tell me where is the error by your eye, you can immediately tell that the error is in the 6th bit, which is, instead of receiving it 1, I received it 0. But since the receiver does not know V nor E, you just know R. So you need to perform literally several complex processes in order to detect the error. And from there, you add the error sequence to the received vector R to get the estimated vector V. So this is one of the approaches that you can use in order to detect the code word that you have received from the channel. Now you detected the code word. What will you do next? After detecting the code word, you need to map this code word to the message signal. How do you map this? Using the generator matrix, because V is equal to U multiplied by G. So if you want to know U, you can say that it's equal now to G transpose, G inverse multiplied by V. Or you can use a mapping table. Which way you prefer depends on the capabilities of your system. If you want to avoid using lookup table, you can use the inverse. But if you find the inverse to be complex to be found, you can prefer to use the lookup table method. So with this, we can stop here for this lesson, and we can continue next time with the other detection processes that can be used at the receiver side. So thank you very much for your attention, and see you in the next lesson.